So welcome to the Block 2 live feedback session. So please do put some stuff in the chat. Tell us who you are and a little bit about yourself. Let us know what country you're calling in from and your institution. I'll run through a few housekeeping rules before we start. So please mute yourself when you're not speaking. If you can, please switch on your video if you have sufficient bandwidth. Please include your full name in the participant list. You can see all the participants if you select gallery view. As we go through the session, please do put any questions about anything in the chat that arise. There'll be part of the session at the end where we'll cover all these questions and there'll be chances to feedback. So put your questions in there and we'll get to them. You can use reactions to engage virtually, and we will use some polls at the end of the session, but these will be anonymous. And yes, please don't share any sensitive or personal data in the chat panel. The session is recorded, so it will be available for access afterwards. So if you don't want to be filmed, then please remember to turn off your camera at the start. Okay. So our agenda for today is as follows. We're going to start with an overview of the modules, of all 4 modules in Block 2, which Usman will lead. And following this, we'll have feedback on the big assignment, which was included as part of the modules, which is assignment 2.3, with which you'll lead. We're going to then go through some of the quizzes, and we'll do a live session on the quizzes for 20 minutes. I'll leave that one. And then George, if his connection allows, will lead a session on taking your questions and feedback about the material itself. And we'll finish with some open discussion of the course itself. So rather than the material, but how you found the course and what you would have liked included and how long it took you and so forth. So Usman, are you ready to start?
Sure, Dave, sure.
Thanks very much.
Thank you, Dave. Thanks very much. So I will give a little overview of the topics. I know you already went through this, but just to give you an idea, why did we put this course together? You can move to the next slide, please. So in this class, we was covering the key climate concepts, the climate system and its predictability, the probability nature of the weather, and lately some question on the probabilities. So this is to reinforce and to facilitate the co-production. You should know the language that we use. That's why we cover in the first class, 2.1, the key climate concept, like what is the difference between weather and climate observation, data collection, how to collect data, what is the difference between seasonal and triennial variabilities, what is lead time in forecasting, natural variabilities, climate model, and there's uncertainties, climate anomalies, climate change. Those few things that you need to know in order to start the course. And then in 2.2, we went further and developing the climate system and their predictabilities. What are the drivers? What makes the climate works? Why do you have the climate behave in such a way that is predictable? So that because the driver of the climate variability. And then we look at the teleconnection and predictability, how things are related together. And then the best teleconnection that we know is El Nino and Southern Ocean. And so I know everybody knows that ENSO, La Nina, the MJO, Modern Julian Ocean, the IOD, and the Atlantic Meridional Mode. And then in 2.3, please, if you can move quickly to the next one. 2.3, we talk about the probabilistic nature of weather and climate information. Anybody who is dealing with this climate information knows that things are highly probable, there is not deterministic per se. So that's why I was talking first of the source of uncertainties, why climate and weather are uncertain, have some uncertainties. And then we talk about how those uncertainties can be quantified by a state-of-the-art climate model. How can we, in our tools, our best guess, we call it the climate model, how can we make the forecast and using and putting in those uncertainties, and then using it, and we formulate it usually in terms of probabilities forecast, you know, up to the model of the output, you know, what is the likelihood. I think you will go deep onto that. And also the last one is a interpretation of probability forecast. That's very important to know how to interpret. What does the probability really mean? How do you translate it into, you know, action or and the last model that we did, 2.4, is a measurement of forecast skill. How good is your forecast? If you give a forecast, how good it is. And for that, we start with the purpose and requirement of forecast verification, you know, reliability and sharpness, those definition, the relationship between action, trigger, threshold, hits, and false alarm. Those are terms we use. Hit rate, you know, how do you get a good forecast, and false alarm rate, how do you miss it? And how to estimate the expected number of hits and false alarm rate given a specified value of hit rate and false alarm ratio. And we finish by sampling variability and other uncertainties which might make forecast verification different from real world outcomes. So this is overall what we was trying to cover during this course. We'll go now in detail into the quiz. Thank you, Dave.
Thanks, Usman. That's a great overview. So next session, we're going to turn to Richard, who's going to give us some feedback on assignment 2.3. So Richard's going to run his own slides. So I'm going to stop sharing, and I'll ask you to share your slides, Richard. I think you might still be on mute, Richard.
Good, thank you. Thank you very much, Dave. Welcome everybody. I'm Richard Graham from Met Office. Thanks everybody for going through the model 2.3 and for making your submissions on that. And I'm just going to go through and give a flavor of the responses received and also some comments about the kinds of things that we were sort of looking for, if you like, for these questions. A little reminder of what they were. For some of you, it'll probably be quite a long time since you first did the assignment. So there were 4 questions on uncertainty and ensemble forecasting. This module, of course, was about the probabilistic nature of weather and climate information. So uncertainty is absolutely central to that. And we looked at ensemble systems, and then there was a little bit of kind of practical, if you like, to come out of theory and look at some actual systems to find the horizontal resolution of a few systems and also the forecast ensemble size. That was assignment 2. And then assignments 3 and 4 were really more about sort of, you know, co-production, if you like, with users and the sorts of things that can come up when you're discussing probabilities and interpreting, you know, how you might act on a probability. And the first one was the context. There was a severe drought in progress, and the forecast for the upcoming season had the highest probability for the wet tertile category. So what advice can you give? What cautions should be given? And then the fourth one, again, sort of co-production type scenario. The forecast probabilities are equal for all of the 3 categories, 33, 33, 33%. Equal chances. So what advice can be given there? The fifth one was kind of, you know, more of a exploratory thing. And this is the experiment with dropping a flimsy piece of paper, which buckles and slides as it falls through the air and is very unpredictable. And looking at that as an example of a complex system and how complex systems can be sensitive to initial conditions. So just an overview. 45 assignments were returned, and thank you very much, everyone, for those. There were 2 I couldn't look at because they were, I think some quizzes had been submitted by mistake, but 43 of these I've looked at, and generally the quality has been, really good, and thank you. Some quite detailed responses to some questions, and clearly a lot of you know quite a bit about drought management and things like that. Undoubtedly more than I actually know, because I've never been in that particular discipline. The overall conclusion I drew is that most were either very well acquainted with the subject before you started, or you actually did learn quite a bit from the block 2 here. So more details then. Assignment 1, so this is the one where we did the 4 questions. And the first one is repeated there. What features of the climate system help us manage the forecast uncertainties and give useful information? And I've divided things up here into what I call an unequivocal yes. That's what we were looking for. Second column is yes, but incomplete. And then I've kind of put a third column for everything else, which is like there were some, potentially good answers, but non-inspected ones, and others that, you might consider perhaps not quite right. But yes, everybody was, clear about it's the climate drivers that really give us our predictability. They change slowly. And I've cut and pasted many of these phrases here from your assignment. So that's why they're in bulleted form like this. They drive slowly, which increases their predictability. They change slowly. And so IOD are key amongst them. They're more predictable than the atmosphere. MJO was mentioned quite a bit, and yes, that is important. Perhaps less so it's less predictable right out on a seasonal timescale, but certainly for sub-seasonal prediction, this is very important. And teleconnections were also mentioned by many. Teleconnections we sometimes think as being all part and parcel of the driver thing, so sometimes we don't actually refer additionally to teleconnections. They're sort of part of the driving process, but they are very important. And then there were, coming to the middle column, many people sort of focused rather than focusing on the first column, were saying things like, well, we can do it because we've got climate models and they're realistic. Well, yes, we do need climate models, but even if they're very realistic, we wouldn't be able to get far if there weren't such things as the climate drivers in the real atmosphere, real world. So it's not quite as fundamental as the climate drivers. Other things were, yes, we have observations, an observation system to start the models. And some mention things like the longitude, latitude of the locations and the tilt of the Earth's axis. Of course, these do determine the mean climate in places, but they won't help you with the climate variability. It's the drivers that control the variability. So these things are yes, but not complete answers. Others mention the traditional indigenous knowledge methods. Yes, they are used, but it wasn't really what I was looking for. This was more about ensemble systems. Some mention the tercile categories, coming to the third column. Those, I mean, in a sense, the very broad description in tercile categories kind of encapsulates the precision that we have. And so, that is not a wrong answer, perhaps an unusual answer. And there is also one where we can manage the uncertainties because we can compare this year with what happened in other similar years. So this is getting to the analog forecasting method. And I don't really think that is like managing the uncertainty personally. So that's a response I wouldn't really have thought was quite right. Moving on to assignment question 1, question 2. Why is it necessary to express forecast information in probabilistic terms? So again, I've got my 3 columns here. Absolutely yes, the climate system is complex. Coming to thinking again about assignment 5 with the dropping piece of paper, small initial errors can create very big differences once you halfway or all the way through your forecast. So that's absolutely fundamental, I think, to this question. Others expressed it like with the chaos aspects of the atmosphere and climate. And this, of course, works against the predictability that we have just reviewed, that is the main source of predictability. And those are the kinds of things I was looking at. Actually, the most common answers weren't that, although some did mention it. Many were kind of focused more on the model imperfections and the initial condition uncertainty. And that is all part and parcel of it. But in this occasion, it's more the complexity of the system. You can imagine if you're dropping that in assignment 5, if you did assignment 5, if you drop instead of a flimsy piece of paper, you drop a solid hardback book in the same way. You could have the same errors when you start off, but a small error is not going to make much difference. You could drop it from some slightly different positions and it would still fall on the floor in about the same place. So those model imperfections and initial conditions are important, but don't overlook the fact that it's the climate and complexity that is a key feature. People were saying we do it because we have to quantify the uncertainties. That's true. Looking at the middle column now, and it makes for better decision making. All these things are correct and true, but it wasn't really the core thing that we're looking for in the assignment. And there wasn't really anything unusual or wrong in the responses there. For assignment 3, question 1, this is where we were looking really for the model imperfections, the 2 key sources of uncertainty. And I won't go into details here. Everybody really got this, so that's great. Model imperfections and the initial condition uncertainty. Someone did kind of call me to task looking at the 3rd column and say, you forgot one, you forgot about the uncertainty in CO2 emissions, which is true. Of course, that is an uncertainty, but less important when we're thinking in terms of the seasonal forecasting. The 4th question, what are ensemble forecasting systems? And more or less everybody, gave me a very full and detailed answer of this. So, and that was almost 100% of right answers. So yes, a collection of forecasts with the same target period, designed to capture the prediction uncertainty, and the ensemble distribution can be used to estimate probability of events. So that's great. I won't go into more details. Now, assignment 2 was where I asked you to go in and look on these websites for the horizontal resolution. And more or less everybody, again, got this completely correct. So well done. I didn't ask for the glossy 5 ensemble size. I've written it in there just for information. It's actually 42. Of the 1 or 2 that responses that weren't quite right, I think it was just a sort of a mistaken reading. There is a column there that gives you the height of the top model level. And so some had mistakenly chosen that value, which is 80 for ECMWF, 85 for glossy. And there again, remember that the forecast ensemble size is different from the hindcast ensemble size, and usually smaller. And 1 or 2 had mistakenly looked at the column that has the hindcast ensemble size, which is 25 for ECMWF and 30 for the German BWD. For those interested, some did answer that the glossy 5 ensemble size is only 2. because that is what it says on the website, but that's not right. Well, it's right in the sense that we run 2 members every day, and then we wait for 21 days before we use them, and we collect them all up. And 2 a day for 21 days makes 42. So it's moving on to assignment 3, where we're looking at, you know, advising your stakeholders, ministries, for example. And we set up a scenario where I've shown the red circle. There had been a severe drought and it was in progress. And the next forecast was coming up with a 45% chance of above, 35% of normal, and 20% of below normal. So on the face of it, you know, a very favorable looking forecast. What advice can you give to resilience planners, and what cautions should be included here? Now, of course, the answers to this are very case specific and country specific as well. So I'm not saying that what I'm going to say is right answers, but these are just some thoughts. So looking at the yes column, we can advise of a favorable forecast. These again are taken from responses you made to me, but there is a caution that needs to be added, because the joint chance of normal and below is 55%, which exceeds the chances of above. And of course, you know, there is a high risk if below should happen, and there's a 20% chance that it will happen, because there is already a drought in the country. So maybe because of the circumstances, some extra caution needs to be drawn. Preparations could include, or plans should include this lower chance of the drought continuing. Of course, the floods may complicate the impact of drought if it does turn out to be a wet season, as the highest probabilities suggest. And a cautionary would be that adaptive measures implemented for drought should continue really until there is signs of alleviation. Now, the middle column, where I kind of reserve for those responses that are kind of, you know, more or less said above normal is going to happen. It's highly likely, which is not really the case at 45%. And so these are what I've listed in the middle column are kind of typical responses, you know, if you were absolutely certain that the above normal case would occur. The unusual ones in this case really were, there were some that would advise their ministries, yes, the drought's going to end, you can anticipate wet conditions. Personally, I would say that is, you know, a little bit too confident with just a 45% chance of above normal. There were a few, maybe there was some lack of clarity in the question, but a few did respond saying that the 45% chance seemed to be taken as a high chance that the drought would continue, but maybe there was a bit of lack of clarity in the question on there, I'm not sure. One nice response said, get an opinion of an independent expert to what they think of the forecast. One that was interesting and I hadn't before. One thing you can look at in this context is these risk matrices that show the likelihood, you see on the going up the left-hand side here, and the impact, this time expressed in household financial burden of the drought. And you see the risk is highest when the likelihood of the event is high and the impact is high up here. In our case, with 20%, the chance is perhaps quite small, but because there has been a drought ongoing already, you might say impact would be really quite high if that 20% chance realized. And so your risk is, you know, in the high category. So it's just a kind of way that you can bring together the probability and the impact of the event should it happen, even though it's a low chance. Assignment 4 was a similar one, but this time there was no context given. It just said that the forecast is for equal chances. What advice now can you give? So this is over here where we have, or maybe even over this side where you have 33, 33, 33. So again, my yes column was don't ignore the possibility of below normal, which is obviously a risk for drought. It's 33%. Prepare diverse strategies that cater for all three categories. Yes, these are all good things. Be prepared for the worst case. Again, very good advice, I think. And there are lots of steps, prudent steps that can be taken, which I won't go through all of them. The ones that are quite often stated, but I personally think is not really good advice, is that, you know, prepare for normal conditions. Because normal is the middle category. Okay? It kind of excludes below normal and above normal. And actually, they're all equally likely to happen. So to say prepare for normal conditions could be misleading. It's not really what the forecast says. Another response was, this is not a rainy season. Now, it is true that sometimes forecasts where there is no rainy season are expressed 33, 33, 33. But we should remember that it could be still a wet season coming up, and you could still have, if there is a lot of uncertainty, 33, 33, 33. So it doesn't necessarily mean that there is no rainy season in the period coming up. Someone else said the only option is to follow climatology, which kind of is true in the sense that, you know, if you want to know the probabilities of the three terciles, that will tell you 33, 33, 33, but it's not really telling your stakeholder anything new, I think. So I think the kinds of responses on the left are better. Some people came in with sort of longer term measures here, which I should say, and as I said, some were clearly expert in drought management, but these were really kind of longer term measures that wouldn't have time to take effect for the upcoming season. So my final comment there is, you know, don't forget this risk matrix. It's, you know, it can help you to remember that even if something is a low chance, if there is a high impact, you know, you should probably be including it into your advisories with your stakeholders. The final one, then, assignment 5. So this was more, you know, perhaps a little bit of fun, serious fun. Dropping the sheet of flimsy paper. So my time's up, but we're almost there now. Most thought this was really easy to do and instructive. Many thought it would be instructive also to stakeholders to introduce the ideas of complexity in the climate system and how that kind of means that we have to use probabilities. Many users would rather we didn't use probabilities. A few, though, did spot that, you know, it would need to be done in the right way, because, you know, it could reduce the confidence in seasonal forecasts, because it looks rather like a guessing game when you're dropping this piece of paper. And most also thought that it could be a good icebreaker for workshops with stakeholders as part of the user engagement and co-production process. I asked for ideas on how to improve it, and, you know, there were some really thoughtful and great suggestions here. I didn't have time to list all of them, but some were, you know, you could use an electric fan to one side to stimulate the climate driver pushing things to one side. It wouldn't be completely deterministic because of the complex fall of the paper. You could put buckets or lines on the floor to represent terciles or other categories. You could repeat the process several times to find the so-called ensemble mean. Maybe there might be a way that you could introduce the effect of forecast lead time on this. I'm not sure quite how you do that, might be possible. And there were quite a few other imaginative ideas on this as well. So many thanks for those, and I hope you enjoyed doing that. I've always found it myself quite a a good way to do in, at least in climate workshops. So that's me finished. Thank you very much again. I'll hand back to Dave.
Thanks, Richard. That's great. Hopefully that was useful to everyone. I'm really interested to hear interesting to hear your responses. Yeah, particularly great ideas about the piece of paper game. I could imagine that there's some interesting things that could be done there. Now, let me just bring up my slides again. I have it on. So I'm trying juggling multiple windows at once, running a Zoom session. Okay, here we are. Right, let me just share my screen. Start video.
I take it there will be some time for questions at the end. Is that right, Dave?
Yeah, there will be. After this session, there'll be a session about feedback, which George will be running. Share screen. Here we go. Okay, there we go. So which slide is that? There we go. Can you see my screen?
Yes.
Great. Okay, so what we're going to do now, I thought we'd, rather than having a static session where we sort of review all these quiz questions, because there were a lot of quizzes across the different modules, designed to just sort of test your knowledge at the time. But these answers weren't recorded, so rather than just sort of running through them, I thought we might try something new and hopefully a bit more interactive, in that we will going to rerun some of the quizzes live for the first time ever with a Zoom poll. And see how that goes, so we can get some live feedback and sort of maybe focus some extra explanations. So don't worry, these are it doesn't matter if you get these wrong, and it's not a test. It's just to review the material, and all of your answers. Zoom does record it, but they're going to be completely anonymous, so don't worry about that. Right, here we go. So we're going to have 3 different quizzes, each one for module 2.2, 2.3, and 2.4. Now, let's start with module 2.2. If I open a poll, to launch poll. Now you should have some questions popping up on the screen, and I'm going to run through them on the slide. So we'll run through the 3 questions for module 2.2 first, and you can put in your answers as we go, or you can run through them all if you want to run ahead. But we'll go through the 3 questions, give you a chance to submit all your answers, and then we'll run through the answers. Okay, so question 1. The question is, what is a climate driver? Is it A, a regional pattern of rainfall, B, a process in the climate system which provides predictability, or C, the name of a global climate observational network? That's question 1. I see there's already some answers coming in. So question 2, what is a teleconnection? Is it a pattern of convection in the Pacific Ocean? A forecast of seasonal average conditions made several months ahead? Or C, a causal link between a climate driver and remote regional climate? I feel like I'm on a quiz show here. This is great. Chris Talent. And finally, question 3 of 3. Which climate driver is most relevant for subseasonal prediction? Is it A, ENSO, B, the IOD, or C, the MJO? I'll give you well, there's already quite a few answers coming in. So that we have 17 participants, so there's maybe 4 conveners here. So wait for a few more of you to have a chance to put your answers in. Let's give it a minute. Need some quiz music here. Okay, so we've got 12 out of 16 people have voted. I'm not sure, perhaps the conveners are not voting. So if you're about to submit, go quickly. Otherwise, I'll end the poll in 3 seconds, 2 seconds, 1 second. End the poll. Okay, let's share these results. Right, I can share these results now with you, and I'm very pleased to say that 100% of people got question 1 right. A climate driver is a process in the climate system which provides predictability. Well done, everyone. So that's an example on the slide is El Nino, ENSO in the Pacific, showing the warming of the central and eastern Pacific, the shift in the Walker cell. Okay, so question 2, again, 100% of people got it right, 12 out of 12, well done. So what is a teleconnection? That is a causal link between a climate driver and remote regional climate. And then finally, question 3, which climate driver is most relevant for subseasonal prediction? The answer was the MJO. We had, most of you got that right, 75%. Some people said ENSO. It isn't, I mean, ENSO isn't irrelevant for subseasonal prediction. You know, the state of El Nino is still important at those shorter lead times for up to a month ahead. But really, it's the MJO which is giving us that subseasonal predictability. Okay, well, that was great. Thanks everyone. You did very well. I'm very pleased with that. So, module 2.2. I'm safe to say that you did very well there. That went in. So let's go to module 2.3. Right, I'm going to launch the quiz now. There are 2 questions here. So, and these are based on the seasonal forecast maps, these tercel maps that you've already seen today. So, question 1, you need to look at the map. Look at zone 1, which is the green zone, and tell me which has the highest chance of occurring. Is it A, above normal rainfall, B, near normal rainfall, or C, below normal rainfall? That's question 1. And then question 2, bit of a tongue twister here, so have a think about it. In zone 1, again, the green zone, is above normal more likely to happen than not happen? So we've got 6 out of 17 people who've completed it so far. So we'll give another minute or so. Okay, so we've got 12 out of 17 now. So 12 people were the same number who voted last time. So perhaps that's the total number. Oh, another one. So we've got 13. So I'll give you 10 more seconds in case if you want to get your answers in. 5 seconds. 4, 3, 2, 1. End poll. Okay. So let's look at some answers. Right, question 1. Which has the highest chance of occurring? Now, to answer this question, you have to look at the numbers in zone 1. So we've got 3 numbers here. Each one represents probability of A for above normal, N for normal, B for below normal. So here, A is 45, N is 35, and B is 20. So the highest is A, which is 45. So the answer is above normal rainfall, A. And most of you got that right. 77% got that one right, which is great. Some said near normal and others below. One said below normal. But what we're looking, so perhaps you may have looked at the wrong zone. Zone 3 has the highest chance of below normal, but it's zone 1 we're looking at. The green highest chance is above normal, which is 45%. Okay, question 2. Looking at that same zone, is above normal more likely to happen than not happen? So what I'm asking there is, what's more likely, above normal or something else? Now, something else would be normal or below normal. So the way to what, so we know all of those probabilities add up to 100%. So, there's different ways to work that out. One, you could say, well, above normal is 45%. So everything adds up to 100%. So we know that everything that's not above normal must add up to 55%. So 100 minus 45. Or you could say, what's the probability of normal or below normal? And you can calculate that by adding those. So 35% for normal, 20% for below normal would total up to 55%. So the answer there is no. Above normal is less likely to happen than not happen. So there's, although above normal is the highest probability category out of the 3, if you consider the other categories together, those 2 are more likely than above normal. I think so. In terms of answers, about half and half said yes and no. So maybe that wasn't. Maybe the wording was a bit tricky there. But it's also a difficult point sometimes to realise that even though that category is high, it's not a sure thing. It's really far from a sure thing, and it's a caution against interpreting those probabilities deterministically. So rather than looking at that and say, oh, look, hey, above normal has 45, it's the highest, therefore we think that's going to happen. Well, actually, it's less likely to happen than actually to happen. So a bit tricky there. Okay, last set of questions. We're just about on time. We've got 6 minutes left in this session, so I'll launch the quiz now. So both of your questions are on this slide. So there's 2 questions. Let me launch the poll. There we go. Question 1. So this is the forecast verification. I think these ones are probably a bit the trickier ones out of what we've seen so far. So question 1 is related to these 4 figures. So if you remember from the module, these 4 figures are what we call reliability diagrams. So these are telling us how reliable a forecast system is. So we've got 4 systems here, A, B, C, and D. And each of those has a reliability diagram, which is the red lines, and a sharpness diagram, which is these blue bars here. And now the question is, which of the systems has slightly overconfident probabilities, but the highest sharpness? And then question 2 is about hit rates and false alarm rates. So question 2 is, a flood forecast system has a hit rate of 60% and a false alarm rate of 40%. What is the chance the next time a flood is forecast, it will be a false alarm. Is it A, 20%, B, 40%, or C, 60%? A bit trickier now. Only 3 people have voted so far, so I'll give you a couple of minutes. Okay, so we have 11 people voted. So there's a few more voters who might be waiting to finish off their questions. Let's give you 15 seconds. Okay. Last chance, and let's end the poll. Okay. So let's go through some answers. First one, most people got this one right. That's really great. I mean, these are tricky. These diagrams can be really confusing to understand, but 64% of you picked the same, let's pick the correct answer, which is C. So what we're looking for here is, so a system which has slightly overconfident probabilities, but the highest sharpness. Okay, so if you recall, reliability is measured by these red dots on the main diagram, and we're looking for the slope of that line to lie along the diagonal if it's reliable. So if it's lying perfectly along the diagonal, it's perfectly reliable. So we can say, well, A is quite flat, in fact, it's the flattest, so that's the least reliable and very overconfident. B is very reliable, so that's probably the most reliable. But we're also looking at sharpness. So sharpness is these blue bars. And these blue bars indicate how often the model is issuing probabilities at different levels. So the bars here correspond to the same probability levels you see on the x-axis here. So this lowest bar is about 0%, the highest bar is about 100%. So you can see that it's not giving those probabilities, the system B is not giving those probabilities that frequently. In fact, the most common probability is about 30%. So this kind of shape, we would say that's quite low sharpness relatively to these other systems. So compare that to C, which is the correct answer, which has very high frequency of issuing very low and very high probabilities. So the probabilities that come out of C are very sharp. In fact, they are the sharpest. D are also somewhat sharp, but C is the sharpest. And as you can see from we're also looking for slightly overconfident. And you can see, yeah, the red line, the red dots are, they're slightly below the diagonal. They're not flat, so there is some reliability in those probabilities, but they're slightly overconfident. So the answer is C. So 64% of people got that right. A few people said B and one person said D. So B is not the right answer because it's not very sharp. And D is a reasonable answer. It's because it is slightly overconfident and there is some sharpness, but it's not the highest sharpness, which is C. So final question of this session.
Dave,
Hi.
just to interrupt, there's one question in the or request in the chat to give more explanation on the overconfidence and sharpness. I mean, should we do that at the end? You can finish the quiz. Yeah.
Okay. Yeah. Maybe I'll just do question.
Samuel will come to you.
Thanks for your question, Samuel. So just once we finish this section, George is going to run a session on questions and answers for the whole module, and we can answer any questions you have about if you want more information. So we'll come back to that one in a minute. Thanks again for your question. So our final question on the quiz is about the flood forecast system. So we've got a hit rate of 60% and a false alarm ratio of 40%. What's the chance that the next time the flood is forecasted will be a false alarm? Now, this is maybe a slightly tricky, not a trick question, but there's no real calculation required on this one, because what we're looking for is the chance the next forecast will be a false alarm. And now, if you recall, false alarm ratio tells you exactly that. So false alarm ratio is, you can see the equation down on the bottom if it helps. So false alarm ratio is the percent of a positive forecast. So in this case, the percentage of flood forecasts which were false alarms. And so it's simply just the answer is 40%. So 55% of you got that one right. Some said A and one said C. So someone's just asked, Nanjono, could there be a working for the percent answer? Well, actually, in this case, there's no working out to do. All the solution is simply reading the value of false alarm ratio. So maybe I'll take a moment to run through again the material. So this was the concept is hit rates and false alarm ratios. And to calculate those, you need to first calculate a contingency table, which is shown here in the top right, where you look at all of the forecasts and you say, well, in this case, you're talking about action, but you convert all of your forecasts to either a forecast of an event or not an event. So did the forecast say there's going to be a flood or not? You look at all of those forecasts where they said, yes, there will be a flood, and then you compare those to the observations. And for those forecasts where the flood did occur, we call those a hit. And for the flood forecast where the flood didn't occur, we call those a false alarm. And then we take the other part, yeah, all those other forecasts which said there weren't going to be a flood, there wasn't going to be a flood, and we say of those, when did the flood? Did any of those get followed by a flood? And if they did, we call those a miss. And the remainder, where there was no forecast of a flood and no flood occurred, we call a correct rejection. So you can categorize all of your forecasts into those 4 quadrants: hits, false alarms, misses, correct rejections. And once you have that contingency table, you can calculate those 2 metrics, which are the hit rate and the false alarm ratio. So the hit rate is the percentage of events, so in this case, the percentage of floods which are correctly anticipated. So to calculate that, we have to calculate the total number of floods, which is the sum of hits and misses, and say, well, what percentage of those were hits? So hits divided by hits plus misses. In this case, the hit rate was 60%, so we would say, well, 60% of floods are correctly forecast. And then the next metric is the false alarm ratio, which is the percentage of forecasts which were false alarms. So in this case, we say, what's the total number of forecasts? Well, that's the total number of flood forecasts. We calculate that by adding hits to false alarms, and then we say what percentage of those were false alarms. And in this case, our false alarm ratio is 40%. So we're saying, well, 40% of positive flood forecasts were false alarms. That gives us 40%. So that's how you calculate it. The question itself was really just, didn't require any calculation, is just correct interpretation of what false alarm ratio actually means. Okay, so most of you got that one right. And if you didn't get that one right, maybe you can, it's a tricky concept, so perhaps it might be worth going back over the material and having another go at some of the exercises. Okay, so we are running a little bit late, but that's the end of that section. So George, if you're there, can I ask you to unmute, and you can help lead the section on questions and feedback about the material. So we have maybe say 15 minutes, or if you want longer, we have longer. But if you have any questions about any of the material covered, any extra clarification, then please either raise your hand and unmute, or you can put it in the chat. And George, if you're there, could you unmute to field the questions and ask the conveners what their answers are? Okay, and I know that George was having some connection problems earlier. And he's still muted, so if you are there, George, could you try and unmute? Okay. Well, in the meantime, I mean, this is for you guys. So so please, if you have any questions, do just you can raise your hand, or you can just unmute and ask a question. Please feel free to speak your mind if anything wasn't clear, or put it into the chat. Yeah, sure. Emma's asked about the confidence and sharpness. Yeah, so if we're going, that's probably a good idea to talk about. I'm just trying to go back in my. Yeah, so if there aren't any other questions, maybe while I'm speaking, if you want to put anything in the comments, we'll maybe go through the reliability and sharpness again, and the hit rates and false alarm rates. So reliability and sharpness. Okay, so reliability is, as a concept, what we're asking about reliability is, do the probabilities mean what they say? So if the model says 60%, is the chance really 60%? If it says 20%, is the chance really 20%? And how do you know that? Because the probability that comes out of a model is just that, it's the output of a model. There's no guarantee that probability means anything, that means anything related to real risk. So we have to verify it. So this is what we do. So we compare all of the probabilities the model ever issued against what really happened to measure the reliability. And what we can come up with is either we say, yes, those probabilities did mean what they say, so 60% does mean 60%, or it means, or they're highly overconfident. So when the model says 60%, maybe every time the model said 60%, the event only occurred 30% of the time. So we know that we could say that those probabilities of 60 were highly overconfident. So that's the concept behind it, and the technical way of doing it is essentially splitting up all of your data into all of the different probabilities. So on this plot here, you might take all the times it said 10% and compare those to the observations, and you plot a plot, and you plot a point here. Then you say 50, all the times it said 50%, plot a point here. Every time it said 100%, you plot a point here. So hopefully you can see if the observed frequency of each probability bin matches the value of the probability bin, then all the points will lie on the diagonal. So if 100% means 100%, it will be up here. If 50 means 50, it will be here. If 0 means 0, it will be here, which is the case for this B here. For A, in general, the observed frequencies were much lower than the probabilities, so it's much flatter. So that's how you create the reliability diagram. That's what the reliability means, and that's how you interpret it. The next point was sharpness, and sharpness is the other aspect. So if your probabilities are reliable, that's great. That means they mean what they say, but in order to actually use them, they need to be different from case to case. Because if the forecast of if the risk of a above normal season is 33% on average, if your seasonal forecast system always says 33% every single year, year after year it says 33%, well, that would be completely reliable.
Hello, I'm here. Sorry.
Hello, George.
Sorry,
Hi, George.
sorry.
Hi. So if that system would be perfectly reliable, because if you take all of the probabilities of 33%, it happened 33% of the time, but it would be completely useless because it wouldn't be able to change your management year to year. You know, in order to change your decision making, the probabilities need to show something different from case to case. So sometimes it goes up to 60%, or sometimes it goes down to 20%. So it says, oh, this year the chance has increased to 60%. Well, that tells you something. That tells you maybe you need to take some extra precaution. Or it goes down to 20%, and you might think, well, we don't need to focus on this hazard as much this year. And so that's sharpness. So that's the other aspect, and you need both of them, because if you have a sharp forecast, which is giving you lots of bold probabilities, 90%, 100%, 0% chance, if it doesn't have reliability, then it's completely useless. You know, if 90% if it still occurs, if it doesn't occur 90% of the time, it occurs 33% of the time. And if every time the model says 10%, it occurs 33% of the time, then it's completely useless. It's almost dangerous. So you need both reliability and sharpness. So that sharpness is, it's kind of simple. It's just what kind of probabilities does the model give over time? Is it always giving the same thing, or is it giving a range of things? And that's what we show in these little blue histograms here. So the bars, so these are showing the frequency with which the model gives different probabilities. So for A, you can see it issues probabilities across the whole range. For B, you can see most often it gives this middle category here, this 33%, and very rarely it gives probabilities over here. For C, you can see that there's very high chances it's going to give a probability of 100 or 0%, so that's a very sharp forecast. Okay, so that's reliability and sharpness. We've already had some feedback about the course itself in the chat, so that's great. Thanks very much. We'll just do a very quick poll. This is now, rather than the content itself, we'd like to get your feedback on how the course was to use. So I'll launch a little poll here. So there's just a few questions. Again, it's completely anonymous. So question one would be, how long did you need to be online to complete the module? 1 hour, under 1 hour, 1 to 2 hours, or over 2 hours? And then question two was, how long did it take you to complete one assignment? So there's under 1 hour, 1 to 2 hours, or more than 2 hours. And the final question, have you found this course understandable? Yes, no, or somewhat. So if you can just add your answers there. It's completely anonymous, so feel free to say whatever you like.
Dave, may I make we're getting quite some good feedback in the chat, so I think you're the host, just to check to save the chat. I'm not sure how you do that, but I think you can.
Oh yes, I can. Great idea.
Thanks everyone for the feedback coming through the chat.
So if there, I mean, as well as that, if there are any other additional comments, please do put them in the comments, or you can say something now. If there's any areas you found difficult, or if there's any areas you found enjoyable.
There's already been a couple of comments at 2.3, 2.4 a bit long.
Mm-hmm. Yes, I think that's certainly compared to the earlier mod 2.1 and 2, they are long. Yeah, and I can see in the polls coming through now, 10 people have voted, and everyone's saying it's at least one hour, and 50% of those responded have said it's over 2 hours. So that's quite a long time for one module. Okay. A range of answers about how long it takes to complete one assignment, but 90% of people have said they found the course understandable, which is great. One person has said somewhat, which is equally great.
But it would be useful to have some feedback on level of understanding before you started the course.
Yeah.
If you could type in the chat about your whether you were already very familiar, a bit familiar, or not familiar with the material before you started the course. That would be useful to know.
So let's just make the point, suggested some more incentive or more hands-on skills to actualize this practically. That's a good point. Yeah, I mean, it can be the challenge with some more of the theoretical material to make it more hands-on and practical. Again, Emma highlighted the should we prepare activity as part of 2.4. Well, that's what we've tried to do. I mean, the example in the video. So hopefully most of you have had a look at that. But for those that haven't, it's an activity that you can play with stakeholders or anyone, which tries to make physical these ideas of hit rate and false alarm ratio. So the video is just it's just me at my desktop moving around pieces of paper. But in reality, we played it with stakeholders, and where we get them all standing up and give them forecasts, and they can decide to act or not act, and they get hits and misses, and they move around the room, and so maybe less of that could be something to think about if you're looking for something a bit more hands-on to understand these kind of concepts. But yeah, it would be great to hear any ideas you have, because we're always trying to innovate and trying to make it more understandable, because it's clear that some of these concepts, mathematical concepts, can risk being a little bit dry unless you try and liven them up a bit. So any ideas you have would be very gratefully received. Great, thanks. Some positive comments there. Thanks, Drake and others. And John. Thanks, John.
Dave, I was just going to, it's Emma here. I was just going to make one comment. I think it's really interesting to see this in practice online. And while you've got that excellent film as a resource for people to go back and look to, and I would really suggest doing that, maybe we could also run through that exercise somehow within a session, just thinking how we can, further revise these feedback sessions. I still find it incredibly difficult to get this one in my head. I know I'm not mathematical, but I wonder if it would be good to go through some examples, if it were possible, online and include it in the live feedback session. But that's for future.
Yeah, it was an interesting idea. I mean, there's all these possibilities coming up with the Zoom and polls and Menti and other things. And yeah, surely these kind of things are, you could imagine a live interactive virtual game to do some of these things, but yeah, how exactly to do that would be something to work out. But whilst we can't be in the same room, that's what we've got to do. So I think it would be great to to develop that idea. Okay, so 11 people have voted, so that hasn't changed for a little while. So I think I'll end the poll there. And I think that's probably time to close the session. We're just 5 minutes over. Thank you all very much for your time. I hope you found that useful. Yeah, we have recorded the session, so that will be available, and we'll share that with all the participants so that you can rewatch whenever you like. And of course, the materials from the course are still available if there's concepts that you want to go over. So I will end the poll there, and I'll end my video to say goodbye. So thanks everyone for coming. I hope you all enjoyed it, and we'll see you soon, and good luck with the rest of the module, and have a great day.
Yeah, thanks from me to everybody. Richard, thank you very much.
Thank you very much to everybody, and
some nice feedback and some instructive feedback also.
And just to encourage everybody to tune in again in about 2 weeks when you've done the next modules in the course, which will come online, which have just come online at the beginning of this week. So we've got the next sessions coming up soon, and look forward to seeing you there. Thank you.
Thanks everyone. Thanks Dave for hosting. Thank you. Bye everyone.
Bye.